Hello, hi one and all. Myself, it's V Deepika, working as an assistant professor in EC department from KG Reddy College of Engineering. Okay, now today let us discuss about the new topic, which is nothing but your bipolar junction transistor. Okay, I know. I think everyone is familiar about your BJTs. Okay, now let us discuss about the few topics about your BJTs. Okay, now coming to the introduction of your bipolar junction transistor, either transistor, it's nothing but a three terminal device where the three terminal names are base, emitter and collector. As we are having three terminals, we can use in it can be operated in three configuration. Okay, now according to the configuration, it can be used for either voltage as well as your current amplification. Okay, so the amplification, why we are named this transistor, why why exactly we named it as transistor, means why the amplification in the transistor is achieved by passing the input current signal from a region of a low resistance to a region of high resistance. So this concept of transfer of resistance has given the name transfer resistor transistor. Okay, so there are two types of transistor. First one is unipolar junction transistor and the second one is bipolar junction transistor. Okay, coming to your unipolar junction transistor, if the current conduction is only due to the and one type of carriers, the majority carriers, then it is called as unipolar junction transistor. Okay, if the current conduction in the BJT, okay, it is due to the minority carriers as well as the majority carriers, means either holes or electrons, both electrons and holes, then it is called as BJT transistor. And this BJT, the output is controlled by the input current. Therefore this BJT is also named as current control device. Okay, there are two types of BJTs, NPN as well as PNP. Okay, coming to the advantages of the transistors. Okay, when coming to the advantages, the main advantage is nothing but it is very smaller in size. Okay, and it is having higher efficiency as well as it does not require any filament power, and its operating voltage is also very low. Okay, now let us see the structure of your PNP and NPN transistor. Coming to your NPN transistor, when one P region has been sandwiched between the two N regions, it is called as an NPN transistor. Okay, here the first terminal here we have named as emitter, and the middle region we have named it as base region, and the last region we named it as collector region. And the regions between this N and P, the connection is called as junction. So here we are having three regions, so we will have two junctions. These junctions are also named it as depletion regions or barrier potential also. Okay, here in the case of N region, the majority are of your electrons, and in the P region the majority carriers are of your holes, and in this N region at the collector side, electrons. So it is an NPN transistor. This is the structure of your NPN transistor. Coming to your symbol of your NPN transistor is similar like this, where here when the just see the arrow symbol, if the arrow symbol is directed towards the emitter terminal, then it is called as an NPN transistor. Okay, and whereas coming to the PNP transistor, when the N region has been sandwiched between the two P regions, then it is called as PNP transistor. The emitter region, base region and collector regions remains the same, but here in the case of here P region, the majority of holes, and in here electrons and here holes. Okay, the direction is towards here, just see the symbol of your PNP transistor, the arrow direction is towards your base. It means that here total due to the holes itself, mostly the majority due to the holes, the whole current will be passed, so that the arrow mark lies towards your base current. So when you go design for different for major circuits in like in VLSI, when you use the circuit symbol, it implies that you are using NPN transistor, where the conduction is mostly due to your electrons, whereas when you use this one, the current conduction is due to your holes. So by making this arrow directions proper only, you can say that whether you are using the a PNP transistor or NPN transistor. Okay, now let us discuss about the operation of your BJT. Okay, when coming to the BJT operation, okay, so when first let us discuss the transistor without applying any external voltage to it. Okay, that application of some external voltage to any device is called as, external voltage is nothing but called as biasing. So when you are not applying any external voltage, it is called as unbiased transistor. Okay, this is about your unbiased transistor. So this is two junctions, where two junctions between, first junction is between emitter and base, and the second junction between the base and collector. And here when you are not applying any voltage, still the minority carriers would be, and the majority carriers at this emitter would be like this. Okay, these are the symbols of it. Okay, in this means that with no external voltage. Okay, so during this diffusion process, the depletion region penetrates more deeply into the lightly doped side. Okay, Nama, lightly doped is this one. Okay, so in order to include an equal number of impurity atoms in the east side of the junction, so the depletion region at emitter junction penetrates less in the heavily doped emitter and extends more in the base region, whereas similarly the depletion region at the collector region penetrates less in the heavily doped collector region and extends more in the base region. So the barrier voltage, which is a voltage necessary to cause electrical conduction in a junction, is of two dissimilar materials. Okay, now let us discuss about the next here we have discussed without application of an external voltage. Now let us discuss about the biased transistor when you are applying some external voltage. So this is the circuit diagram of your biased transistor. When you go for your this biased transistor, okay, now in this where you are applying here the transistor, you are applying in such a way that here the emitter base junction, here we are using the NPN region, means what, this total region is of electrons and the P region of holes, and this N region is of conjunction of your electrons. Is it right? Now the transistor actually can be operated in four possible bias combinations normally. Okay, saturation, forward, cutoff, inverse, active. Okay, now normally here this one is of electrons. It means that here when you are, I am applying the external DC voltage in such a way that here I am grounding this base region and making the negative of the external voltage to be applied to the in region and the positive of the region to the here this N region. Here when I am applying this negative to your negative, it means that it is forward biased. When this positive to your negative, it means it your reverse biased. So the application of this external DC voltages to your emitter and collector regions, okay, will give in four regions. Okay, as saturation, forward active, cutoff, and inverse active. Okay, normally the transistors, like cutoff is nothing but when both are of your reverse bias, then it is called as cutoff, and when both are your forward biased, then it is called as saturation. Okay, when this one, the first one is of forward biased and this one is of your reverse bias, then it is called as forward active region. Mostly forward they won't use, it is an active region. Okay, then when this one is of reverse bias and this one is of forward, it is as inverse active. But mostly we will have three regions: active, saturation, and cutoff. So here we have taken in this applying with respect to your active region, where I am making this one as forward biased and where this one as reverse biased. Okay, now let us coming to the operation of the transistor. Now I had made this forward biased by this applying VVD source, and thus the depletion region at this junction will be reduced. That the collector base junction is reverse biased, increasing the depletion region. Okay, nama. Here just see ma. Here forward bias means everywhere the forward biased emitter base junction causes this electrons in the n-type emitter to flow towards the base. So this constitutes this emitter current. Okay. So as this electrons flows through the p-type base, they tend to combine with the holes in the p region. So due to right doping, very few of the electrons injected into the base from the emitter recombine with the holes, okay, to reconstitute the base current IB. Okay, and the remaining large number of electrons cross the base region and move through the collector region to the positive terminal of the external DC source. So this constitutes the collector current. So here the conventional flow of direction means what? Here just see this, actually the current directions would be taken opposite to the flow of electrons. So here the electrons are been flowing towards this side, so they had taken the emitter current towards this side, and here it was towards this side, so had taken in the opposite direction of the flow of electrons. So now just see this also arrow mark directions IE and IB. We can write IE equals to IB plus IC. Okay, so in the case of this is about your NPN transistor, whereas if you take your PNP transistor, just make here PNP and make this one as forward bias and reverse bias, and your total whole direction will be taken, and emitter current will base current and collector current will be opposite towards this side. Okay, next coming to your transistor currents. Okay, so the directions of the conventional currents in your NPN transistors have been shown like this ma. This one is about your NPN transistor, and this one towards your PNP transistor. So it can be noticed that the arrow at the emitter of the transistor symbol points in the direction of the conventional direction. Okay, in both directions you just see here I can write it as IE equals to IB plus IC, whereas here also IE equals to IB plus IC. Okay, now next let us discuss about the transistor current components. Okay, this figure shows the various current components in the PNP transistor which flow across the forward bias emitter base junction and the reverse bias collector base junction. Okay, now just see this ma. Here the emitter current which consists of the whole current IPE and as well as INE. Okay, the ratio of the holes to the electron currents IPE by INE crossing the emitter base junction, okay, is proportional to the ratio of the conductivity of the P material to that of the N material. Means the conductivity is proportional to your doping level. If the doping is more, the conductivity more, and if doping is less, conductivity is also less. In commercial transistor, the doping of the emitter is made much larger than the doping of the base. Okay, so the holes crossing the emitter base junction and reaching the collector base junction constitutes the collector current IPC. So not all the holes crossing the emitter base junction JE, okay, so reach the collector base junction, but some of them will combine, okay, combine with the electrons in the n-type base. So since base width is very small, so most of the holes cross the collector base junction, okay, and very few recombine constituting the base current, okay, IPE minus ICE naught, IPE minus IPC naught. Okay, now just see this one ma. Here I have discussed about IPE and IPC. Now let us discuss about this IC naught reverse saturation current. So when emitter is been open circuited, means when this emitter current has been 0, so and hence IPC equals to 0. So what happens in such condition, the base and the collector act as reverse bias diode, and the collector current equals the reverse saturation current, which is nothing but IC naught. So I can write IC equals to IPC minus IC naught. Okay, now there is a little difference here. IC naught equals to IC plus IPC, I said IC plus IPC. IC naught. Whereas we are having another current ICB naught, ICB naught, which is nothing but reverse collector saturation current. Reverse collector saturation current. Okay, ICB naught. This one I have discussed. Here it is the current when the emitter current is 0, that is when emitter is open. Means what? ICB naught is nothing but IC naught only for physical transistor. But it is defined as the current when the emitter current is 0, that is emitter is open. Means what? Emitter is open circuited. Since the emitter is open, no carriers are injected from the emitter into the base and the emitter is 0. Okay, so as ICB naught is defined for physical transistors, it constitutes the leakage current flowing around the junction. Okay, around the junction and across the surfaces. Okay, due to this ICB naught is greater than your IC naught. It is due to the across the junction as well as your surfaces also. So ICB naught is always greater than your IC naught. Okay, Nama. Now this is about your transistor current components. Now let us discuss about transistor, how transistor can be used as an amplifier. Just see this diagram, how the transistor can be used as an amplifier. Now here the load resistor RL is in series with your series with your collector supply voltage VCE. Okay, for this circuit a small change in the input voltage between the emitter and base, okay, causes a relatively large emitter change IE, delta change IE. So the fraction of change in IE which is collected and pass through this RL is defined as alpha dash. Therefore the change in the output current which is nothing but alpha IE, and the change in the output voltage which is across the load resistor, this change can be represented as RE dash into delta E. Okay, now under these circumstances what happens? The amplification can be written as what? The output by input. So the output delta V naught by delta Vi can be written. So which is nothing but alpha dash of RL by RE dash. So this, from the above discussion, it can be clear that the dynamic resistance of this emitter junction is defined as Vt dash by IE. Okay, where IE is nothing but quiescent emitter current. So now if you substitute RE dash as 40 ohms and alpha dash as 1 and RL equals to 12 ohms and A equals to 50, A becomes 50 directly. Okay, it means that it means that what? From it means that what I already explained. Please let me know the answer. Students, please think. Okay, I'll just give you the I'll say you. Here I had said that amplification is nothing but change in the output voltage by change in the input voltage. Change in the output voltage is nothing but delta V naught by delta Vi. Okay, that equals to, I said that delta V naught is nothing but alpha dash RL into delta of IE. Alpha dash RL into delta of IE by where change in input voltage is nothing but RE dash into change in of IE. Okay, when you just implement it, then you will get alpha dash of RL by RE dash. Okay, now this dynamic resistance, this is nothing but RE dash, it can also be written as Vt by IE. Vt by IE. Okay, now in this, if you substitute alpha dash as 1, RE dash as 40 and RL as 2 kilo ohms, then we will get A equals to 50. So it is, from the above discussion, it is clear that the current in the low resistance input circuit is transferred to the high impedance output circuit. So the word transistor, which originated as a contraction of the transfer resistor, is based on the above explanation. So alpha dash can be written as, can be said as the ratio of the change in the collector current to the change in the emitter current, at constant collector to base voltage, and it is also called as small signal forward short circuit current transfer ratio, which is where alpha dash. Okay, Nama. So this is the main application of your transistor. Okay. Let us discuss about the next configurations in your next PPT. Thank you.